Assalamu alaikum and welcome to Cambridge Chemistry channel with Sarwat Ahmed. In this video I will be solving 9701 May June 24 question paper 4-2. So let's start. Question number 1, describe the trend in the solubility of the sulfate of magnesium, calcium and strontium. Explain your answer. Magnesium sulfate is more soluble. This is magnesium, calcium, strontium. So most soluble is magnesium sulfate, then calcium sulfate, and least soluble is strontium sulfate. Solubility of the sulfate decreases down the group as delta H lattice energy and delta H hydration enthalpy change of lattice energy and enthalpy change of hydration is going to decrease down the group, but enthalpy change of hydration decreases more than enthalpy change of lattice energy and delta H solution, and delta H solution becomes less exothermic. So that's why strontium sulfate is least stable and solubility of sulfate decreases. Sulfate decreases down the group, decreases down the group. So these are the for 1 mark for this. Second mark, that delta H lattice energy, enthalpy change of lattice energy, enthalpy change of hydration decreases down the group. And first mark is this, second mark, and third mark is light enthalpy change of hydration decreases more than lattice energy, and fourth mark for enthalpy change of solution becomes less exothermic. Define lattice energy. It is enthalpy change when 1 mole of ionic compound is formed from its constituent gaseous signs under standard conditions. For example, this is sodium ion, gaseous sign, plus 2Cl negative gaseous sign to form sodium chloride. So this is ionic enthalpy change of lattice, delta H lattice. State and explain the main factors that affect the magnitude of lattice energy. Ionic radii increases, lattice energy less exothermic, and ionic charge increases, enthalpy change of lattice energy increases. It means ionic radius and ionic charge is the main factor which affect the magnitude of the lattice energy. D part, table 1.1 shows some energy changes. So this is data of the question is given, and the question is Born-Haber cycle can be used to determine the lattice energies of the ionic compounds. Complete the Born-Haber cycle in figure 1.1 for potassium sulfide. Include state symbol for all the species. This is enthalpy change of formation 2K solid, and this is 2K gaseous, enthalpy change of atomization, and this is enthalpy change of ionization, energy, and this is also enthalpy change of atomization of sulfur. And next is potassium and enthalpy change of this is potassium ion and sulfur in gaseous form. So now electron affinity, first electron affinity of sulfide ion -1, and this is the second electron affinity, first electron affinity of sulfide ion, and then this is the second electron affinity of sulfide ion, and this is enthalpy change of lattice. Calculate the lattice energy of potassium sulfide using relevant data from the table 1.1. Show your working. So enthalpy change of formation is given in the data booklet, that is minus 381, and this is 89.2, 89, and these energies are used in this first delta HF, enthalpy change of atomization of potassium, plus first ionization energy of potassium enthalpy change atomization of sulfur plus first electron affinity second electron affinity plus lattice energy. So by calculating this on calculator we get minus 2116 kilojoule per mole. So this is lattice energy of potassium sulfide. Question number 2, lithium nitrate decomposes on heating in a similar way to group 2 nitrates to give the metal oxide, a brown gas and oxygen. Write an equation for the decomposition of lithium nitrate. So lithium nitrate on heating, it decomposes into lithium oxide, nitrogen dioxide and oxygen gas. The other group 1 nitrate decomposes on heating to form a metal nitrate and oxygen. The thermal stability of these nitrate increases down the group. Suggest why the thermal stability of MnO3 increases down the group. Cationic radius increases, so less polarization of nitrate ions, anions with cations. So that's why thermal stability increases down the group. Acidified manganate ion can be used to analyze solution containing nitrite ion by titration. Excess solution of sodium nitrite to 50 centimeter cube of X is added to 50 centimeter cube of 0.125 mole per dm cube acidified potassium manganate solution. Manganate ions are in excess, all the nitrite ions are oxidized in the reaction. The unreacted MnO4 ions required to 22.50 mole centimeter cube of concentration 0.0400 mole per dm cube of iron 2 to reach the end point. So the relevant half equations are shown. So by balancing these equations, multiply 5 to this equation to balance the electrons. 5 and 2 with this equation and 5 with this. Mole is of manganate ion is 0.125 is concentration into volume in dm cube. So we convert volume in dm cube. 0.125 like this, 0.125 into 0.0500. So these are the 6.25 into 10 raised per 2 minus 3, and mole of iron is 0.0400 into 22.50 divided by 1000. This is 9 into 10 raised per 2 minus 4. So unreacted manganate ions. So this is manganate ions are in excess and this is limiting. So unreacted manganate ions is divided by 5 is equal to 1.80 into 10 raised by 2 minus 4. The mole of manganate ions reacted 6.25 into 10 raised by 2 minus 3 minus 1.80 80 into 10 raised by 2 minus 4. So the answer is 6.07 into 10 raised by 2 minus 3. Mole of nitrite ion by taking mole ratio. Manganate ion is 2 moles and 5 moles of nitrite ion. So we get 1.5175 into 10 raised by 2 minus 2. These are the mole of nitrite ion. Now concentration of nitrite ion, mole is equal to concentration into 250 divided by 1000. So the we can use mole over volume to calculate the concentration of nitrite ion. So mole over volume into 1000, so this is 0.0607 is the concentration of sodium nitrite in X. Table 2.1 shows electrode potential for some of electrode reaction involving manganese compounds. Aqueous manganate ion are unstable in acidic conditions and undergo a disproportionation reaction. The E cell for this reaction is 1.140 volt. So the constant overall equation for this disproportionation reaction, we use this equation and this equation. Anode has this equation MnO4 to form MnO2. No, not this MnO4 negative ion plus 4H positive. This equation, we are using this equation and cathode, and this equation at anode. So this equation for cathode and this equation for anode. So the anode reaction is this: oxidation takes place, and this is reduction takes place at cathode. So the overall equation is 3MnO4 2 minus plus 4H positive to form 2MnO4 negative plus MnO2. So this is proportionation reaction. Disproportionation reaction, because manganate 4 ion is oxidized and reduced at the same times. This is plus 4 and this is 4 to the 8 and minus 1, so that is equal to plus 7. This is oxidized and reduced at the same time. And this is MnO42 minus, this is plus 6, 4 to the 8 and minus 2, that is plus 6. Suggest and explain how the E cell value of the disproportionation reaction changes with an increase in pH. E cell will decrease when pH increase, and when concentration of hydrogen ion decreases, the equilibrium will shift left and E cathode will decreases. So E cell is equal to, now E cell is equal to E naught cathode minus E naught anode. It is a smaller value and it is the mole value. Question number 3.